Hello, my dear students. This is Thursday, and I want to talk to all of the students in the class today, virtual students and face-to-face students, because I am out today. There'll be a sub at school for me this day, so your assignment today is to listen to this brief screencast and complete the questions on the section review that has been assigned in the classroom. So let's get started with introduction of a new topic, the nuclear atom. And you will have a copy of this particular lecture set in the classroom stream. So I'm not sure how expanding the screen works in a screencast. So let me quickly introduce our new topic today so you can get on with your work. Cathode ray tubes, and for the face-to-face students, I'll demonstrate one briefly in class, are the old-fashioned, the component and the basis for the old-fashioned cathode ray tube TVs and computer monitors. Unlike today's modern flat screens, those are the big ones. If you go to the classroom, you will see there's one up above the board. So we now know today that unlike Dalton's theory, which was basically just incomplete, that the atom is divisible and that there are three types of subatomic particles: protons, electrons, and neutrons. And this all started with, J.J. Thomson. He's an English physicist who, around 1900, discovered the electron as he was working with cathode ray tubes. And these cathode ray tubes are hooked up to a vacuum to remove most of the gas in there, so you're at very, very low pressure. But a high voltage is applied across the tube, and the result is, coming from the cathode, a stream of negatively charged particles headed toward the anode. So in this particular view, it would be heading left to right. And he was studying this stream, and he saw that it was affected by magnets. You can see here a picture of an actual cathode ray tube being deflected by a magnet. Here it's actually being attracted up to the magnet. And he also saw it could be deflected by electrically charged plates, and that the stream itself moved toward the positive plate. And since it was attracted to the positive plate and opposites attract, the stream must be a stream of negatively charged particles. And coming from electrical, origin, the term electrons is what stuck. And every atom today, has electrons in it. There's another particle that is a positively charged particle called a proton. And there's a third type of particle called the neutron, which is similar in mass to the proton, but has no charge. And if I can move on here, I can draw, but I don't seem to be able to move. Here we go. We'll go back to this chart with the properties of the subatomic particles. But if you notice, electrons are negatively charged. J.J. Thomson showed us that. And we've measured their charge, but he was unable to measure the actual charge on the electron. He could only deduce the charge to mass ratio. It wasn't until Robert Millikan came along. He was working at University of Chicago, and And he was able to see that although we knew the charge to mass ratio of the electron, we could not determine the actual mass of the electron. And Millikan showed that the charges on oil drops that were extremely small, what we call atomized, and suspended and then charged such that they deflected, he saw that that charge was always a multiple of a certain value. And so that multiple must be the charge of an individual electron. If you got 2 electrons, you got double the charge. If you got 10 electrons, you got 10 times the charge. But he was able to deduce the charge on the electron, and as a result, they were able to take Thomson's charge to mass ratio and, given the charge, determine the mass of an electron, and they're extremely small. It would take 1,840 of them approximately, given the ratios we're using today, to equal the mass of 1 proton or 1 neutron. The largest element has 118 electrons. So in no element is the mass of an electron a significant fraction of the mass of a given atom of a given element. The protons and the neutrons are much more massive, 1,840 times as massive if you look at this table here, and as a result, they are what contribute to the mass of an atom. What Ernest Rutherford discovered was that most of the mass of an element is concentrated in the nucleus. Thomson had a model called the plum pudding model, where you had a sea of positive charge with electrons floating in it, much like chocolate chips in a chocolate chip cookie, or bits of raisins or fruit in what was called the plum pudding model. Ernest Rutherford, he was originally, of course, from New Zealand, but was working. He went to Cambridge, went to, I want to say, McGill University in Canada, and then back to University of Manchester. And at University of Manchester, I've actually been inside his laboratory and been inside the chemistry building there. Beautiful old campus in Manchester. He was working and doing his famous gold foil experiment. And for those in class, if I can find them, I'll show you my gold foil. Gold is amazing in that it can be hammered into extremely thin sheets that are only a few atoms thick. And he was passing a beam of alpha particles through the gold sheet. An alpha particle is 2 neutrons and 2 protons all stuck together. It's basically the nucleus of a helium atom. I like to use Coleman camping lantern mantles for a source of alpha particles. They contain thorium in them and are a great source of alpha particles, which really can't even penetrate more than a very short distance through air and cannot penetrate skin. They're a very safe form of radiation to work with. But what he discovered was that when he passed the alpha particle beam through the gold foil, the great majority of the particles passed through and exposed the film on the opposite side of the beam. But occasionally, rarely, a particle was deflected. And that was picked up in his very sensitive equipment, and sometimes even deflected almost straight back towards the source of the alpha particles. But again, the majority passed straight through. They passed straight through a sheet of metal. And he concluded that the alpha particles over here, alpha, were able to pass through because they, oops, see if I can go. They're encountering atoms that are mostly empty space, and that most of the mass of the atom was concentrated in a very small area at the center of the atom that he termed the nucleus. So, this is the model we use today, and that is what we call the nuclear model of the atom, or Rutherford's nuclear model of the atom. We now know the nucleus is made up of protons and neutrons, and they're surrounded by a cloud of moving electrons, and those electrons are central to our theory, but I don't want to say central because they move around and about the nucleus. How they will be distributed is the subject of our next topic. So quickly, some sample test questions. Which of the following is not an example of a subatomic particle? You should know that there are 3 subatomic particles: protons, neutrons, and electrons. And a molecule would not be a suitable choice for a question like that. The nucleus of an atom consists of protons and neutrons. The electrons exist around the nucleus, and I must say the nucleus is extremely small relative to the total volume of the atom. It's been said that if the nucleus were a fly sitting on second base, the rest of the atom would be the stadium you're playing in. I've heard other comments like if the nucleus were the size of an orange, sitting in the Orange Bowl in California. No, that's in Florida. Sitting in the Rose Bowl in California, but let's say the Orange Bowl in Florida, that the nearest electron to it would be at the very top of the stands. Some of these don't always seem congruent, but I was at a lecture once and someone said if the nucleus were the size of a golf ball, the nearest electron would be a mile away. My point is that the electrons take up all the space, even though they themselves are extremely small. Their orbits or their paths take up a lot of space, and the nucleus at the center of the atom is extremely, extremely small. So most of the volume of the atom is occupied by electrons, but they themselves are extremely small. That concludes our screencast. Please complete the assignment that is posted in your class files. I will show it to you here, and you may go to that. If I can find my Google Classroom here, you will find within your classwork our new assignment, Structure of the Nuclear Atom, with the terminology you need to master and some very simple questions about which particular subatomic particles have mass, protons and neutrons. Electrons, for our purposes, have, because they're only 1/1840th the mass of a proton or neutron, basically have no mass. And of course, here, the electrons have the negative charge, and the protons have the positive charge, there for question 19. And nucleus contains, of course, the protons and the neutrons in a very small but very dense center. So, complete the assignment, hand it in, and we will see you in the next screencast.